The efficiency of a heat engine is defined as the benefit to cost ratio. In the case of a heat engine, the benefit that we get out of it is the work that it does. The cost is the energy absorbed from the hot reservoir because that energy has to be replaced by, for example, burning fuel. So the work over QH is the efficiency of our engine. Now we can rewrite this in terms of heat exchanges only by remembering that the work that's done is the difference between the energy absorbed from the hot reservoir and the energy expelled into the cold reservoir. So we can rewrite the work as QH minus QC. Then finally, with a bit of algebra, we can simplify that expression to the efficiency is equal to 1 minus the ratio of the heat expelled into the cold reservoir divided by the heat obtained from the hot reservoir. So a perfectly efficient engine would not expel any heat into the cold reservoir. Q sub C would be equal to 0 and the efficiency would be equal to 1. However, all real-world engines can't do this. It's not possible for the world we live in, and we'll be talking a little bit more later on about why this is. So next, let's take a look at this example problem. During a complete cycle, a heat engine transfers 2,000 joules of heat from a hot reservoir with 1,700 joules exhausted into a cold reservoir. What is the efficiency of this engine? So let's take a look at this problem. This heat engine is going to be taking in 2,000 joules of heat from our hot reservoir. So Q sub H is equal to 2,000 joules of heat. Then some of that energy gets turned into useful work, and the rest is expelled into the cold reservoir. And Q sub C, we're told, is 1,700 joules. And we want to find what is the efficiency of this engine. So one of the expressions we have for efficiency is 1 minus QC over QH, where all of these heat quantities are positive. So that would be 1 minus Q sub C is 1,700 joules, and Q sub H is 2,000 joules, and so that gives us an efficiency for our engine of 0.15, and it would also be correct to say that our engine is 15% efficient. Other important heat devices are heat pumps and refrigerators. And these are devices that are basically heat engines that can work in reverse. So heat engines follow the natural flow of heat from hot to cold, and heat pumps and refrigerators use an input of work to make heat flow the wrong way from cold to hot. So heat pumps and refrigerators take some amount of heat out of a cold reservoir with some input of work, and then that combined energy gets dumped into a hot reservoir. So a heat pump, one example of a heat pump is if you have geothermal heating. Geothermal heating uses water that's pumped into pipes that are underground, and underground is typically at some temperature, which is a little bit warmer than the temperature of the air in the wintertime. So you have this water, which is still colder than the heat in the room, but the heat pump takes heat out of the water that's been underground, and it takes some amount of heat out of that water and pumps it into the room. So that's how a heat pump works. A refrigerator does something similar. It takes heat out of the inside of the refrigerator, which is cold, and pumps it into the hot reservoir, which would be the room outside the refrigerator. So for both of these devices, we use a slightly different term for evaluating the benefit-cost ratio, and we use a term called the coefficient of performance, I guess because efficiency was already taken for heat engines. but a coefficient of performance is still fundamentally the same as efficiency in that it is a benefit over cost ratio. And what you see as the benefit or the cost depends on the goal you're trying to achieve. So for a heat pump, you are trying to heat a room by taking heat out of a cooler place. Your goal is to heat the room, and so the benefit is the heat that you're putting into the hot reservoir, which is the room. So the coefficient of performance for a heat pump, which has as its goal heating, is going to be QH over W. W is the work that you have to do in making heat flow the wrong way, and that work usually is in the form of electrical power. If, on the other hand, you have a refrigerator, your goal is to cool the inside of the refrigerator, and so the benefit is the QC, the heat that you can remove from inside the cold reservoir. So the coefficient of performance for a refrigerator is Q sub C. And then once again, the cost is the work that you do. One way in which coefficient of performance is different from efficiency is that efficiency for a heat engine is always less than 1. The coefficient of performance for a heat pump or a refrigerator can be greater than 1 because you're putting an amount of heat sometimes into the hot reservoir that is greater than the work that you are doing. So especially for heating, the coefficient of performance is often greater than 1. It means something slightly different from efficiency, but as with efficiency, higher is better.